Today, we're going to be deriving Kepler's third law. Now, in my other video on Kepler's third law, that basically only really accounted for circular orbits. In this video, we're going to make sure that Kepler's third law holds true for elliptical orbits. So how can we do that? Now, before we get into it, let's just remember that Kepler's third law basically states that the orbital period of a planet squared is directly proportional to the semi-major axis of the orbit cubed. So how can we find that this is true for any planet? Now, the way that I'm going to start out with this is I'm going to use what we know from Kepler's second law. From Kepler's second law, we remember that dA over dt is equal to L over 2m. The thing that I'm going to do is we're going to think about the full orbital period of the planet. After one full orbital period, we know that the area covered by the planet is just going to be the entire area of the ellipse. So we can rewrite dA over dt as the area of the ellipse divided by the orbital period. Now we know that the area of an ellipse is just pi AB. So I'm going to replace that with pi AB. Now what I'm going to do is I am going to solve for t squared, because that's one of the parts of Kepler's third law. So I'm just going to solve for t squared. And to start off by doing that, I'm just going to cross multiply first. Then I'm going to divide L on both sides. Now after that, remember, I'm solving for t squared, so I'm just going to square both sides. So this is what we get when we solve for t squared. Now, at first, you might be thinking, wait a minute, t squared is directly proportional to a squared, because 4 pi squared is a constant, the length of the semi-minor axis of an orbit is constant, and the mass of a planet is constant, and the angular momentum of a planet is constant. So is t squared directly related to a squared? Now the thing is, we can't do that. The reason why is because b is related to a, and the angular momentum of the planet is also related to a. In fact, we can show that the angular momentum of a planet is related to a from Kepler's first law. We remember from Kepler's first law that the shape of the orbit of a planet is defined by this polar equation. Now, if we're thinking of the orbit of a planet as an ellipse, then we are going to just set this equal to the shape of the orbit that corresponds to an ellipse. Remember that for an ellipse, the polar equation would be this. So this equation is true as long as the orbital path of a planet is an ellipse. So what I'm going to do is I'm going to write both of these equations in the same form as each other. In other words, I'm going to make sure that this number right here is a 1. So I'm going to make sure that this value right here also becomes a 1. And the way I'm going to do that is I'm going to multiply both the numerator and denominator by the reciprocal of this value, which would be L squared over GM squared. So this is what we get. So next what we're going to do is we're going to try and clean this up so that's in the same form as this expression. So in the numerator, we just get L squared over GMM squared. Now in the denominator, I'm first going to focus on the first term right here. We know L squared cancels out with L squared, GMM squared cancels out with GMM squared. That leaves us with just 1. And right here, for our a cosine theta, it's just a times L squared over GMM squared. So a times L squared over GMM squared times the cosine of theta. So this is, of course, equal to the same thing we had before. So now, both of these expressions for the elliptical orbit of the planet are both in the same form because they both have a 1 right here. That means we can set the numerators equal to each other. So next what I'm going to do is I'm just going to solve for L squared. Here's the thing. E is still related to A. So what I'm going to do is I'm going to just write E in terms of A. Now we know that in order to write E in terms of A, we could just say that E squared is equal to C squared over A squared. Because we know that's what eccentricity is. E equals C over A. Now, again, C can also be written in terms of A. We know that C squared is equal to A squared minus B squared. Now, if you were to simplify everything that's in the parentheses, you would get B squared over A squared. So if we were to just clean this up, we can see that L squared is equal to... So what I'm going to do now is I'm just going to substitute L squared for this into here. So now that we've substituted L squared into here, this is actually really nice for us. And we can see that M squared cancels out with M squared, but even more importantly, we can see that B squared cancels out with B squared. And this is really important because that means we won't have to rewrite B in terms of A anymore, because B is now gone, it's canceled out. So now we can rewrite this side of the equation as this. So we can see that we have t squared equals some constant times a cubed, and as a result, this means that t squared is indeed directly proportional to a cubed. And so this verifies Kepler's third law.